Hi, my name is Raymond Cabrera, and my partner is Ghebrial, and we tested a phenomenon known as capillary action. We observe a phenomenon known as capillary action on a macro scale in our everyday life. We see plants and trees soak up water from the ground and transport it upward against the force of gravity. We've even experienced it in annoying situations such as stepping on a puddle of water with your socks on, causing your sock to absorb the water through capillary action. So what is capillary action? It is defined as the action by which a fluid is drawn up into a small pore space as a result of surface tension. The forces of cohesion between the water molecules and adhesion between water and the material create surface tension, which allows water molecules to migrate upward and sideways against the opposing downward pull of gravity. In light of this information, we chose to hypothesize that capillary action increases with an increase in a material's porosity, as well as with an increase in the liquid's temperature. To test this hypothesis, we used the materials shown here, which include plastic containers, a thermometer, measuring tape, and water shown on the top row, as well as two identical sponges, one gray concrete brick, and one red clay brick shown on the bottom row. To test the effects of a material's porosity on capillary action, we used a more porous gray cement brick on the left and a less porous red clay brick on the right. The difference in porosity can be seen by the surface features of each brick. Our assumption for this experiment is that the more porous brick will have lower capillary action. In this experiment, we placed both bricks into separate containers with 48 ounces of water each at room temperature and let them soak for 30 minutes. Before we discuss the results of each experiment, let's take a look at some governing equations. The first equation shows that the volume absorbed equals the cross-sectional area of a material multiplied by sorptivity and the square root of time. Sorptivity is basically the capacity of a material to absorb liquid by capillarity. Equation 2 is the cumulative liquid intake of a material, which equals the volume of absorbed liquid divided by the material's cross-sectional area. Equation 3 is the wetted length of the material, which equals the cumulative liquid intake over porosity. Algebraic manipulation of this equation leads to an equation for porosity shown in equation 4. This is why we hypothesize that the brick of a higher porosity will have a lower capillary force, because porosity is inversely proportional to wetted length. Now the result of our experiment shows that our hypothesis was correct. Due to the high porosity of the gray concrete brick, it experienced lower capillary action, as you can see by a higher capillary height on the less porous red clay brick. In our second experiment, we tested the effects of liquid temperature on capillary action. We used two identical sponges for this experiment, and we hypothesized that the sponge with the hotter fluid will experience more capillary action. In this video, we placed one sponge in a hot water bath, shown on the right, and the other in a water bath at room temperature on the left. As the video is sped up, you can observe that the effects of capillary forces in action. In this experiment, both sponges were left to soak for 4 minutes. The governing principles behind our second experiment are adhesive and cohesive forces. Adhesion and cohesion affect capillary action through surface tension, which causes a liquid to ascend into a material. Through these definitions, we hypothesize that more adhesion relative to cohesion results in a higher capillary flow. In other words, an increase in liquid temperature would cause a decrease in cohesive forces, resulting in a greater molecular attraction between the liquid and the material, which is why we believed that the sponge absorbing the hotter water will have a higher capillary action. In this experiment, our assumption was incorrect, as capillary action increased at a similar rate in both sponges with different temperatures. It's arguable that the sponge on the right has a lower capillary height, which may be a result of lower surface tension in hot water. Before we conclude, let's take a second to discuss how capillary action plays a role in the microscale world. We see through equation 5 that the scaling law of capillary action is inversely proportional to the density and cross-sectional area of a material. Thus, we see that surface tension at the microscale plays a more dominant role as we decrease in cross-sectional area. Thanks for watching.